Hello everyone, I welcome you all to the lecture series of chapter number 10 from NCERT textbook, that is haloalkanes and haloarenes. So this is lecture number 2. In the previous lecture, that is lecture number 1, we have discussed about how can we prepare uh, the haloalkanes from alcohols. That was first one was the by the Grooves process, then Darjan's process, then reaction with NABR in the presence of H2SO4, then reaction with PCl3, PCl5, and red phosphorus in the presence of X2. Then reaction with silver salt of carboxylic acid, that is Hunstrecker reaction. If the reaction occurs for iodine, that is Berban-Simony reaction, and it yields to formation of ester. And then from alkanes, photochlorination, and then from alkenes, MKR and anti-MKR rule, then unsaturation test for unsaturated compound, then allylic addition. There are 5 reagents we have discussed regarding allylic addition: NBS, NCS, Cl2 at 800 degrees Celsius, Pr2 at 800 degrees Celsius, and SO2Cl2. Let us move ahead to next part, that is from alkynes. So from alkynes, HCl that too we will use, and along with that we put HgCl2. Why? That's just to fasten up the reaction. It yields to the formation of a complex like this, and it is something which fastens the reaction. Further, next one is the halogen exchange reaction, that is Finkelstein reaction and Schwarz reaction. Finkelstein reaction is for NaI in the presence of acetone. Haloalkane is reacted with NaI in the presence of acetone, and it yields to the formation of CH3CH2I plus NaBr. The acetone used here is having two functions. First one is it acts as a solvent here, and second thing, it help in reaction getting completed. Okay, so it basically absorbs NaCl or NaBr formed in the chemical reaction, which according to Le-Chatelier principle shifts the reaction in the forward direction and helps in getting reaction completed. Schwarz reaction, the reaction with metallic fluoride of haloalkane. Okay, so that is Schwarz reaction. Why halogen exchange reactions are needed? The reason is because most of the methods we have discussed in the previous lecture, they were for the preparation of chloro compounds and bromo compounds. Now, if we need to prepare iodo and fluoro compounds, then we need some specific method. For example, in case of photochlorination, if we will use iodine, then it becomes a reversible reaction, and if we will use fluorine there, then that becomes a highly exothermic reaction. So simply we are using here Finkelstein and Schwarz reaction. Finkelstein is for preparation of iodoalkanes, and Schwarz is for preparation of fluoroalkanes. This we have to remember. Next is preparation of haloarenes. Then we are having several different methods, like Br2 in the presence of FeBr3 give rise to Br in the presence of HBr, or you can use here Cl2 in the presence of AlCl3, that will lead to addition of chlorine. Okay, and next is from diazonium salts. Allylic addition, this is similar. Okay, next is from diazonium salt. If you'll talk about diazonium salt, that is benzene having N triple bond N positive, Cl negative. So for preparing diazonium salt, what we need is aniline. Aniline is reacted with HNO2, that is nitrous acid, or NaNO2 in the presence of HCl at 0 to 5 degrees Celsius. This yields to formation of benzene and triple bond NCl, and this is something known as diazonium salt. Here the diazonium salt can be benzene diazonium bromide, nitrate. For example, if this benzene diazonium chloride is reacted with HBF4, then it yields benzene diazonium tetrafluoroborate. So this is also one of the diazonium salt. Okay, so if we will heat this diazonium salt, then it yields to the formation of fluorobenzene uh, along with BF3, and nitrogen gas is formed here. Next is Gutterman reaction and Sandmeyer reaction. What's the difference between two reactions is, if the reaction is having copper in zero oxidation state, if the reaction is having copper in zero oxidation state, then the reaction is Gutterman reaction. Okay. So if we are using Cu in the presence of HCl, or Cu in the presence of HBr, or Cu in the presence of HCl, it leads to the formation of chlorobenzene, bromobenzene, or cyanobenzene. Okay. In all the three cases, uh, we are using here metal in the zero oxidation state, that is copper. And if we are using it in the +1 oxidation state, this reaction is known as Sandmeyer reaction. The same products will be formed. If CuCl in the presence of HCl, this yields to formation of chlorobenzene. CuBr in the presence of HBr, this yields to formation of bromobenzene. CuC in the presence of HCN, this yields cyanobenzene. Okay, if it is reacted with Ki, then it yields iodobenzene. Diazonium salt, if reacted with Ki, then it yields iodobenzene. So this was regarding how can we prepare haloarenes. How can we prepare haloarenes? So for preparing haloarenes, we need diazonium salt, okay, or chloro and bromo, that we can prepare directly by allylic addition, or by bromination, Br2 in the presence of FeBr3, chlorination, Cl2 in the presence of AlCl3. So these all are the different methods for preparing haloarenes. Okay. One thing we have to remember here is, here we are using HNO2, NaNO2 plus HCl at 0 to 5 degrees Celsius. Okay. HNO2 or NaNO2 plus HCl, that is nitrous acid only. So here the starting reagent is aniline. The starting reagent here is aniline. When aniline is reacted with this, then it yields benzene diazonium chloride, and then it happens. Okay. So here the preparation part is complete. Now let us move ahead to the physical properties of haloalkanes and haloarenes. I hope you have understood the preparation part. First thing in the physical properties we will discuss is state. So if I will talk about state, then I can clearly mention here the 1 or 2 carbon compounds are gaseous. Then 3 to 10, 11 or 11 are liquids, and 12 and above are solids. This is the general trend in case of haloalkanes and haloarenes. But a few compounds we have to remember. Okay, that is CH3Cl, CH3Br, and CH3CH2Cl. These are gaseous in nature. These are gaseous in nature. So these three compounds are gaseous in nature, that we have to remember. Compounds having 3 to 11 carbon are liquid, and 12 and above are solids. Okay. These are specifically mentioned in the NCERT textbook. That's why we have to remember them. Okay. Next to this is a discussion regarding boiling point. If we will talk about boiling point, then boiling point in the organic chemistry here is directly proportional to uh, basically intermolecular forces, you can say. And the intermolecular forces we will generally consider here are van der Waals forces. Now, van der Waals forces are the function of molecular weight and the surface area. That's why boiling point is directly proportional to molecular weight. More is the molecular weight of a compound, more will be the van der Waals forces, more will be the boiling point. And it's inversely proportional to branching, because branching reduces the surface area. Because branching reduces surface area. Okay, if branching reduces surface area, and this leads to decrease in van der Waals forces, which due to because of which boiling point is also decreased. So this is inversely proportional to branching. This we have to remember. Now let us have a look at like if it is chlorobutane, and other compound is secondary chlorobutane, secondary butyl chloride, sorry, or tert butyl chloride. So in these three compounds, the branching is maximum in case of tert butyl chloride. This can be numbered 1, 2, 3. So branching is maximum in case of tert butyl chloride. So this is having a minimum surface area. Maximum surface area is with compound number 1, that is butyl chloride. So 1 is having maximum boiling point, then 2, and then 3. So because in the compound 1, that is butyl chloride, it is having the maximum surface area. So this will have maximum boiling point. The molecular weight of all the three compounds is same. So the order we have written here is on the basis of branching. Okay. Next is, if I will talk about density, then CH3I, iodo and bromo derivatives are more denser than water, and then CH3F, and chlorides are also more denser than water, like CCl4, CHCl3, CH2Cl2, H2O. Haloalkanes are partially insoluble in water. If I will talk about solubility, okay, I'm not saying that haloalkanes are insoluble in water. It's just that they are partially insoluble in water, or they are very less soluble in water. Let me explain the solubility of haloalkanes and haloarenes in water. See, the compound is suppose CH3Cl, okay, and you are solubilizing it in water, H2O, or you can take a compound which is in liquid, CH3, CH2, CH2Cl. Suppose this is the compound and another one is H2O. So one thing is though that solubility is directly inversely proportional to size of hydrophobic part, size of hydrophobic part. This I am talking about solubility in water. This thing we have to remember. Another thing is, if we are solubilizing one chloropropane in water, then what will happen is these AA molecules, suppose CH3, CH2Cl and CH3, CH2Cl, they are having dipole-dipole interactions. Interactions in between them. And here we are having the hydrogen bonding. So whenever the bonds are broken, then energy is needed and new interaction setup will be in between CH3, CH2, CH2Cl and H2O. So suppose this is forming a bond here, hydrogen bond here. Okay. So these new interaction setup are not as much as strong to break the previous interactions, which is hydrogen bonding present in water. So new interaction setup do not release as much as energy, which can break the previous interactions. So that's why haloalkanes are also polar and water is also polar. So why they are just less soluble? Why they are not completely soluble? Polar, polar, like dissolves like, they must be completely soluble. And the reason they are partially soluble is because new interaction setup do not release as much as energy to break the previous interactions, which is hydrogen bonding and dipole-dipole interaction in case of haloalkanes and haloarenes. So the reason is new interaction setup do not release as much as energy to break the previous interactions. That's why haloalkanes are partially soluble in water or very less soluble in water. They are practically basically insoluble in water. Now let us move ahead to the chemical properties of haloalkanes and haloarenes. So this was all about physical properties, which is boiling point, boiling point, density, solubility. One more thing we can discuss here is dipole moment. What is dipole moment? Mu is equal to Q into D. That is, suppose this is a dipole. So if here is a del positive charge and here is a del negative charge, so these two charges are separated by a distance d. So this del positive charge is suppose q and this del negative is also q. So if same charges are separated by distance d, then same and opposite charges are separated by distance d, then that is dipole. And their dipole moment is given by q into d. So more the polar a substance will be, more will be its dipole moment. Here polarity we will relate to the electronegativity. More the electrons halogen can withdraw, the more polarity is. But the other thing we have to also consider is the distance between them. So considering both the factors, the order comes for methyl uh, methyl derivatives are is as CH3Cl is having maximum dipole moment, then CH3F, then CH3Br, and then CH3I. So this is the order of dipole moment we will see here. Why CH3F is having less dipole moment than CH3Cl? Because of this bond length, this D. However, charge will be a dominating factor otherwise. But in case of CH3F, we have to see the distance also. Bond length is increasing in others also, but the dominating factor is charge. If there are two factors, then what is the dominating factor that will be the deciding factor? So we can say that in case of CH3Br, CH3I, and CH3Cl, the dominating factor is charge, while in case of CH3F, the dominating factor is distance between them. That is rivalry. Now let us discuss about nucleophilic substitution reactions or chemical properties of haloalkanes and haloarenes. Let us come to that part. Chemical properties. See, the CX bond, the nature of CX bond is it's something polar in nature. Okay, so the halides show nucleophilic substitution reactions. The first thing we will do here is we will write the different reactions for which halides are showing. Then we will have a look at the mechanism later on. Okay, so what will happen here is nucleophile is there, then there is a leaving group which is halogen, and it will lead to formation of CNU, and the leaving group which is halogen will leave from here. Okay, so halogen is a leaving group. It is sometimes represented by L. This is not necessarily halogen, and since we are studying haloalkanes and haloarenes, that's why you can say this is halogens. Okay, so the nucleophile here can be negatively charged, okay, and maybe neutral, or maybe sometimes positively charged too. Negatively charged like OH negative, aqueous KOH, this will substitute. Okay, neutral like NH3, so this will form RNH2. So this is a neutral nucleophile, or KCN, AgCN. These are also CN negative is an, okay. So these are the neutral and negative nucleophiles. Now let us have a look at different nucleophilic addition reactions, nucleophilic substitution reactions. First, reaction with aqueous KOH, RX reacts with aqueous KOH to form ROH. Then reaction with R dash O negative Na positive. This is also known as Williamson ether synthesis. In this reaction, what will happen is RX plus RO negative Na positive. This will yield ROR dash. So R dash can be primary, secondary or tertiary, allyl or vinyl. But this must be necessarily primary. This must not be vinyl or phenylic. Means this X halogen group must not be directly attached to benzene ring, or means this bond must not have partial double bond character in this simple bond. This single bond must not have a partial double bond character. Means R cannot be a vinylic group or simply benzene ring. This can't be simply a benzene ring, phenyl group or vinylic group. This can't be. This can be a benzyl or allyl group. No problem with that if the carbon is primary. In case of secondary and tertiary, this causes elimination and leads to the formation of alkenes. This we have to remember here. Okay. The same reaction we will be studying in ethers also. There we will be discussing in detail. Next is reaction with KSH. RCl reacts with KSH to form RSH plus KX. Fourth, reaction with RS negative Na positive. Then it is RCl gets reacted with R dash, S negative Na positive, give rise to RSR dash plus NaCl. Fifth, reaction with RC triple bond, R dash, C triple bond, C negative, Na positive. This is important for preparing the alkynes directly from haloalkanes. RCl plus R dash, C triple bond C negative Na positive. This will yield R C triple bond C R dash plus NaCl. Next to this is reaction with KCN. This is important. This is one of the example of ambident nucleophile. Okay, so RCl reacts with KCN to form RCN plus KCl. Next is reaction with AgCN. Then what happens here is a ionic bond leads to the formation of Cn negative ion, because of which RCN is formed. In the reaction with AgCl, here is a covalent bond, because of which the lone pairs present or nitrogen are the attacking, okay, which makes nitrogen as the attacking species. So the compound formed here is RNC, that is isocyanide plus AgCl. This is because of the covalent bond present between Ag and Cl. So this is an example of ambident nucleophile, that is Cn negative, where C and N, a single nucleophile is having two attacking sites. A single nucleophile is having two attacking sites, so that is known as ambident nucleophile. But definitely it can bind through one also, one only at a single time. Next is reaction with KNO2. So RCl reacts with KNO2 to form RONO plus KCl, or RCl is reacted with AgNO2. Then what is formed here is RNO2 plus AgCl. Okay, so again NO2 is also an ambient nucleophile. Here the compound formed is nitrosoalkane, and this is simply nitroalkane, or this is isonitroalkane. Ninth one is the reaction with silver salt of carboxylic acid ester, RCl, reacts with R2CuLi, dialkyl copper lithium. So this yields to formation of RR dash plus R dash Cu plus Li. So this is the part of Corey house synthesis, which is used for preparing unsymmetrical alkanes. 10th one is reaction of RCl with R dash C double bond O OAG. This gives rise to formation of esters plus AgX. So that was all regarding the different kind of reactions. Next we can mention here is the halogen exchange reactions also. RCl in the presence of NaI and acetone yields Ri plus NaCl or NaBr, which is absorbed by acetone. This is something known as Finkelstein reaction. And next RCl reacts with any metallic fluoride, say Hg2F2 or CuF2. This yields to formation of RF, fluoroalkane. Okay, so this was regarding the different nucleophilic reactions. However, more we can add to the list. RCl reacts with ammonia to form RNH2. Basically, this form is RNH3 positive, Cl negative. When this is heated, then it yields RNH2 plus HCl. This can happen if RCl is in excess. Okay, if RCl is in excess, then RCl can react further to this. Then this can yield to formation of R2NH, and it can react further. That can yield to formation of R3N, and then RCl can react further here with the lone pair present over nitrogen. Then it will yield to formation of R4N positive Cl negative. This is quaternary ammonium salt. And if Rx is taken in excess, then this reaction is known as Hoffman's exhaustive ammonolysis. Okay, and or either we can take here RCl plus NH3. If NH3 is in excess, this will make one step only here, that is RNH2 plus HCl. And we have to heat also it afterwards. Okay, then it will to formation of RNH2 plus HCl. So this is something known as Hoffman's ammonolysis. Okay, and so that's all about the different kind of possible reactions. And the next part to it, SN1 and SN2 mechanism, that we will see in the next lecture. So thanks for watching the video. Have a good day. Bye bye.